the things we need to think about at present is the situation in Japan, horrific situation, getting hit with an earthquake, a tsunami, and a nuclear event. I'll come on in a second, a little plot of the growth of nuclear, but recognizing that the horror that nation is going through, I just want to peel out the one piece of impact on energy. So you now see a loss of confidence in nuclear. Is nuclear really a way to go? And so what we see at this point is this tranche, this green tranche here, which is quite a significant player, is now under question because of an event like this. And it's not an isolated event. If you actually look at people, there are many people not particularly fond of wind. They like the idea of wind, but certainly not within sight of their window. Lots of good discussion about bio. Is bio good, bio bad? Is it stealing crops? So there is always lots of tension as you bring in new technologies. So why is it that we don't see more wind and solar and well, biomass actually grows quite well? And it's, again, a little piece of work that was done by our researchers, actually they're based here in these buildings. They went back to historic data, and this will take me a second to do. There's only one worse graph in this one, so it's the second worst graph. So this is 2010, roughly this line here is where we are now. So this is time across the horizontal. And on the vertical is a logarithmic scale of energy delivery. So every time you cross one of these lines here, it's 10 times bigger than below. So it's not twice, it's 10 times. It's a logarithmic scale. And what they did was they looked at delivery in this red line. This is the growth of nuclear, the addition in terajoules per year, the addition of nuclear between 1960 and here 1980. We see this logarithmic growth year on year, and then it starts to flatten. And then the next one, logarithmic growth in LNG, and Andre will talk about that. Logarithmic growth in biofuels, logarithmic growth in wind, almost all the same slope. Kind of interesting, this one. And that slope is energy grows at about an order of magnitude, gets 10 times bigger every decade. That's 26% year-on-year growth through these decades. Now, if you in your own companies can imagine every year getting 26% bigger, 26% more staff, keeping the revenues flowing in, keeping staff growing, keeping the HR systems running, the finance systems, it appears to be something about the limit at which technologies can sustainably grow. There's something about this. There's also a point where they break over. And this is when they hit what we call materiality, when it's about 1% of the overall supply of energy in the world. Then the growth tails off from exponential to, oops, sorry, that's the worst one. It tails over when you're about 1% of the world's energy. So what we're witnessing, when I go back, all of these energies up here are going through that logarithmic growth. They are growing an order of magnitude every decade, which is a phenomenal growth. It's just you're starting from such a small base, competing against energies that are delivering 80 million barrels a day. So when you try and get your head around it this way, it's not illogical that those energies are taking a bit longer to develop. So, is that making sense, that one? How yeah.
If you talk about 80 billion, how much is the total market in something else, so we can...
So 80 million barrels is about a third of the total of the world's total energy. Yeah. So if we go back to this one, we see that oil, which is the red, is about a third. Certainly, it's about a third today, just over a third. It remains a bit. So you start to see these energies start to become material, whereas nuclear already is material. It's already made it to that point. It's already sort of rounded that curve quite some time ago. And it's a little bit difficult to see. There's a flat spot here in the nuclear world where the build almost stopped. You take that down 1979, it was 3 Mile Island, then 1982, 86 was Chernobyl, and that was a flattening there. So this is all about the supply side of things. And I want to take you now to another view, and I promise this is the worst one you're going to get. It'll take me a second to describe this one. Imagine this is the world, and this is how the energy is used in the world. On the left side are all the different kinds of energy that we consume. In the middle tells us how that energy is used. So if, for instance, and the thickness of the line is roughly proportional to its position in the world energy mix. So third oil, quite a bit of coal, natural gas, so on. You push this in. The oil, for instance, you follow it through, it's primarily for transport. Almost all oil goes for transport, a little too expensive to use in power these days. Whereas coal is almost exclusively for electricity generation. So what we do is we push all this energy in, we either make electricity, we heat our houses, we run an industry, we drive our cars, and at the end, we get a ratio of how efficient we get. And what we find is that all the energy we push in, 55% of it is wasted. 55% waste. Transport sector, 85% waste. Aviation, 92% waste.
So you define waste, it's waste.
Waste heat. So 15% of the energy actually moves the car forward. And Amy Lovins goes that extra bit. He goes, well, if you take the weight of the driver versus the weight of the vehicle, then you're moving all the steel for a 70 kilo person. So it's even less optimistic. So there's a whole other world. Instead of us pushing energy into the global market, there's a thing about wasting less. What can you do with being more efficient? So we've got to work both of these, more energy in and more efficiency out. So I'm getting a nod and a wink, so I better move on. So where do we end up? And this is a very schematic sort of diagram. This is the energy that we needed in the year 2000. That's the amount of energy, is the near tripling of the energy that we'll need in 2050. Way up there. When I talked about energy production and delivery, all of those energies growing over time, at ordinary supply rate, it would take us up to about this level. Using ordinary efficiency measures that we're aware of, it could bring us down to this point up here. It takes us to about here. By 2050, we've got this zone of extraordinary opportunity or misery. Because we don't have enough energy to take us to the top, and we don't have enough efficiency to take us to the bottom. And this is where the tension is going to start to be. Because we just don't know right now how this is going to be bridged. Okay? So, you probably don't know, but I've been showing great restraint. For the last 5 years, I've been leading the climate change group in Shell, corporate climate change, and I haven't mentioned it yet.
Good.
And I'm going to get thrown off. So, I haven't even mentioned that there's a climate constraint in all of this. Today, we're at about 390, 380 parts per million. At Cancun, they tell us we can go to, Cancun, they agree 450 would be the point. So we're looking at about 60 ppm that can be put in the atmosphere. And we saw a few slides back, most of the energy is coming from oil, from gas, from coal, all of them CO2 emitters. So in that case, if we are going to deliver the energies, we're going to need all the efficiency we can get and more. We're going to need all the renewables. We're going to have to press that growth curve. As worried as we may be about nuclear, we're going to need it. We're going to need this carbon capture and storage with all of the oil and the gas and the coal. We're going to need it as well. We're going to need the forest to do their part. We're going to need natural gas. And I'm going to hand over to Andre in a second to touch on that one. And most importantly is how people will behave through all of this. Because what I observe with great admiration, the way Japan, the stoicism, the order, the way people manage a shortfall. And that is a world very much like a blueprints. We call in our world of scenarios a blueprints world where there is a structure, there is a sharing of a limited resource, there's a willingness at a national scale to allocate. There is a chance. There's a chance, and I'll let you guess estimate what kind of chance the world has of having that stoic behavior. The other one is a scramble world, where it's a dash. You use what you can, when you can. You don't worry about the environmental constraints. You just make sure you keep your growth going. These are two end members of the way the world can progress. We can scramble, or we can blueprint. Clearly, what was going on in Copenhagen and Cancun, it was an attempt to get to this blueprints world. And we do see little elements of it. We do see elements around the world, the European trading scheme for CO2 and so on. Clearly, this is a world that we prefer. We would love to see a blueprints world. We do have indications of early blueprints, some will scramble. These are the two things that the two end members to think about. What is it that we do? There are lots of things that we could do. Well, let me start at the bottom. Efficiency. All of that waste going on, we're trying to improve the efficiency of our own operations. You saw vehicles, for those of you who have a vehicle, 15% efficient. When we deliver fuel to the forecourt, we've used about 10% of the energy, 15% to get it to the pump. So when you drive up, you take possession of 85% of the remaining energy. So what you arrive in as a vehicle, the way you drive that vehicle is very important. So similarly, we have to look at our own efficiency. We're developing carbon capture and storage with a number of demonstration sites. We've got a big biofuels program, one of the biggest blenders of biofuels in the world, as well as developing first and second gen biofuels. And Andre is going to take us through this natural gas world. It's a new boom, and he'll tell you a bit more about the details of that. So I've run desperately over, so Adrian, thank you.
Yeah.
Andre, if I can ask you to...